I'm Rayesh Uppal, founder of IDST. We bring you sharp insights and foresight on emerging tech, defense, and security. Let's dive in.
Water is the thread that connects life, exploration, and the future of humanity in space. For decades, NASA and other space agencies have followed a simple mantra: follow the water. And for good reason. Wherever we find water, we find the possibility of life. But in today's new space race, the search for water isn't just about answering the age-old question of whether we're alone in the universe. It's also about survival and expansion. Water is the single most valuable resource for sustaining astronauts on long missions. It can be purified for drinking, split into oxygen for breathing, and even transformed into hydrogen and oxygen to power rockets for journeys deeper into space. In other words, water is the currency of the solar system. On the Moon, frozen deposits at the poles are being targeted as a cornerstone for future lunar bases and refueling stations. On Mars, evidence of ancient rivers and subsurface ice suggests the planet once had flowing water and could still hide reserves today. And beyond Mars, the icy moons of Europa, Ganymede, and Enceladus may hold vast hidden oceans beneath kilometers of ice, warmed by tidal forces and geological activity. If confirmed, these worlds could be prime habitats for microbial life. But finding water in space is no easy task. It can exist as vapor, ice, or liquid, and much of it is buried deep beneath rock and ice. Drilling through kilometers thick crusts in places like Europa is a nearly impossible engineering challenge. Spacecraft face extreme cold, intense radiation, and low gravity, making operations risky and short-lived. Traditional instruments like cameras and radar help us map the surface, but they struggle to peer deep into alien worlds. That's why NASA and researchers are turning to breakthrough quantum technologies. One of the most promising is quantum magnetometry, a revolutionary way to detect subsurface oceans without ever breaking through the ice. Instead of drilling, these sensors measure faint changes in magnetic fields as they interact with hidden layers of salty water. On Europa and Ganymede, Jupiter's strong magnetic field induces secondary fields in their oceans. By analyzing these subtle signals, scientists can map the depth, size, and even salinity of alien seas. This isn't science fiction. NASA is already preparing to launch the Europa Clipper mission in the 2030s, equipped with a magnetometer designed to probe beneath Europa's frozen shell. Enceladus, famous for its geysers that shoot water vapor into space, is another prime candidate for exploration with these sensors. The power of quantum magnetometers lies in their sensitivity and efficiency. They are smaller, lighter, and use less power than traditional instruments, making them perfect for spacecraft, CubeSats, and deep space probes. They even self-correct over time, ensuring reliable data collection on long missions far from Earth. And the search doesn't stop in our solar system. With the James Webb Space Telescope and future quantum-enhanced instruments, astronomers are now detecting water vapor in the atmospheres of exoplanets hundreds of light-years away. Some of these planets orbit in the habitable zone of their stars, where liquid water could exist on the surface, a tantalizing hint that life may not be unique to Earth. The implications are staggering. Water isn't just a resource. It's the foundation for building human colonies, fueling interplanetary travel, and perhaps one day confirming we are not alone. The next decade may bring answers that reshape how we see the cosmos and our place within it. As we continue this journey, one truth stands out: the future of space exploration will flow where the water leads.